Submarines. These underwater vessels hold a certain mystique. They are stealthy, powerful, and capable of diving to incredible depths. Imagine exploring the ocean's depths, miles below the surface. Picture yourself in a metal tube surrounded by water. How do submarines, those underwater behemoths, stay submerged? How do they navigate the vast, dark expanse of the ocean? These underwater vessels, essential tools for both military and scientific exploration, rely on a delicate balance of physics and engineering. Their ability to control their buoyancy, withstand immense pressure, and navigate the deep ocean is a testament to human ingenuity. Join us as we unlock the secrets of these underwater marvels. The mystery of a submarine's ability to submerge and resurface boils down to a fundamental principle: buoyancy. This force determines whether an object floats or sinks. It all depends on the relationship between the object's weight and the weight of the water it displaces. An object less dense than water, like a beach ball, experiences a buoyant force greater than its weight, causing it to float. Conversely, an object denser than water, like a rock, sinks. Submarines, however, have a trick up their sleeves. They can manipulate their buoyancy, switching between floating and sinking at will. This is where Archimedes' principle comes into play. This principle, named after the ancient Greek mathematician, states that the buoyant force acting on an object submerged in a fluid is equal to the weight of the fluid displaced by the object. Submarines use this principle to their advantage by adjusting their overall density. They have specialized compartments called ballast tanks that can be filled with either water or air. When the ballast tanks are filled with air, the submarine becomes less dense than water, causing it to rise to the surface. To dive, the submarine takes on water into its ballast tanks, increasing its density and causing it to sink. Imagine a bathtub filled to the brim. You step in, and water spills over the sides. Archimedes figured out that the amount of water displaced is equal to the volume of the object submerged. More importantly, the weight of that displaced water is the key to understanding buoyancy. He realized that an object submerged in a fluid experiences an upward force, buoyancy, equal to the weight of the fluid it pushes aside. Submarines are equipped with ballast tanks, essentially giant lungs that can be filled with either air or water. When these tanks are filled with air, the submarine is buoyant, ready to bob on the surface. But when seawater floods the ballast tanks, the submarine's overall density increases, making it heavier than the water it displaces, and it sinks. Think of it like a seesaw. On one side, we have the weight of the submarine itself, its hull, engines, crew, that suspicious-looking periscope. On the other side, we have the buoyant force, pushing upward with a strength determined by how much water the submarine displaces. When the submarine is on the surface, the seesaw is balanced. But to dive, the balance must be tipped. By carefully controlling the amount of water in the ballast tanks, the submarine crew can achieve a state of neutral buoyancy. This means the submarine neither rises nor sinks, but remains at a constant depth, like a fish hanging motionless in the water. Understanding buoyancy might seem tricky, but we can visualize it with a simple experiment. Imagine holding a balloon underwater. You can feel the water pushing back, resisting your efforts. That's buoyancy at work. Now imagine letting go of the balloon. It shoots to the surface, propelled by the buoyant force, which is now greater than the balloon's weight. A submarine, while considerably larger and more complex, operates on the same principle. By manipulating its density through the ballast tanks, it can either mimic the balloon, rising to the surface, or defy the upward push of buoyancy and descend into the depths. Picture a submarine, not as a sleek, menacing vessel but as a giant mechanical fish. Now imagine this fish with a special set of lungs, ballast tanks. These tanks, strategically placed within the submarine's hull, hold the key to its underwater acrobatics. When a submarine needs to dive, these tanks are flooded with seawater, dramatically increasing the vessel's overall weight. The once buoyant submarine, now heavier than the water it displaces, begins its descent. To return to the surface, compressed air is forced into the ballast tanks, purging the seawater back into the ocean depths. As the water is expelled, the submarine becomes lighter, its buoyancy slowly returning until it breaks free of the surface. The process of controlling a submarine's buoyancy is a bit like finding the perfect balance on a seesaw. On one side, there's the weight of the submarine itself, its hull, its machinery, its crew, and even the snacks in the galley. On the other side, we have the buoyant force, pushing upwards with a strength determined by how much water the submarine displaces. To initiate a dive, the submarine's crew opens a series of vents, allowing seawater to flood the ballast tanks. As the tanks fill, the submarine becomes heavier and the seesaw tips. Surfacing requires reversing the process. High-pressure air is pumped into the ballast tanks, forcing the seawater out through the vents. As the water is expelled, the submarine becomes lighter, the seesaw tips back, and the vessel rises toward the surface. While ballast tanks control a submarine's depth, its vertical position in the water column, hydroplanes allow it to maneuver, to glide silently through the ocean depths. These small wing-like structures located on the submarine's sail, the conning tower, and stern, act like the ailerons on an airplane controlling the vessel's pitch and roll. When the submarine needs to change depth, the hydroplanes are angled to create a downward or upward force. Angling them down forces the submarine's nose downward, sending it deeper. Angling them up lifts the nose, initiating an ascent. It's a subtle dance, a delicate interplay between the forces of buoyancy, the flow of water over the hydroplanes, and the submarine's own momentum. This balance between ballast tanks and hydroplanes allows submarines to navigate the three-dimensional world beneath the waves. Imagine diving deeper and deeper into the ocean. The weight of the water above you increases, pressing in from all sides. This pressure, immense and unrelenting, is one of the greatest challenges faced by submarine designers. For every 33 feet, 10 meters of depth, the pressure increases by 1 atmosphere, the equivalent of the air pressure we experience at sea level. At a depth of 300 feet, 91 meters, the pressure is 10 times greater than at the surface. This means a submarine at that depth is experiencing a force of over 1,400 pounds per square inch, psi, pushing inward on its hull. Submarines, unlike those inflatable pool toys you tossed around as a kid, aren't designed to expand and contract with changing pressure. In fact, as a submarine dives, the immense pressure actually causes it to shrink slightly. This phenomenon, known as compression, is a testament to the incredible forces at play in the deep ocean. To withstand the crushing pressure of the deep, submarines are built with meticulous care and incredible strength. Think of a submarine's hull as a giant underwater eggshell, designed to distribute pressure evenly across its surface. The shape itself, that iconic cigar shape, is no accident. It's the strongest shape for resisting hydrostatic pressure, allowing the force to flow smoothly around the vessel. Submarines are constructed from special high-strength steel alloys, far tougher than anything you'd find in a skyscraper or a bridge. These alloys are designed to resist both crushing and fatigue, the weakening that occurs under repeated stress. The hull itself is incredibly thick, often several inches thick in deep-diving submarines. Before a submarine ever embarks on a real deep-sea mission, it undergoes rigorous testing to ensure it can withstand the crushing pressures of the deep. These tests, conducted in massive pressure chambers that mimic the ocean depths, are a testament to the meticulous engineering involved in submarine design. Imagine a submarine, sealed tight, being lowered into a giant steel cylinder filled with water. As the submarine descends within the chamber, the pressure increases, just as it would in the ocean. Engineers and technicians monitor every creak, groan, and pressure reading, looking for any signs of weakness or leaks. These tests are crucial for identifying any potential flaws in the hull's design or construction. Even the slightest imperfection, a tiny weld flaw or a microscopic crack, can become a catastrophic breach under the immense pressure of the deep ocean. Imagine yourself in a submarine, hundreds of feet beneath the surface. Sunlight fades into an inky blackness. Familiar landmarks, coastlines, islands, even the stars, vanish. You're enveloped in a world of silence and perpetual twilight, where the only constant is the immense pressure of the water around you. How do you navigate in this alien environment? How do you find your way in a world without roads, signs, or a friendly GPS to guide you? Unlike surface ships that rely on celestial navigation, lighthouses, or satellite signals, submarines must navigate a three-dimensional world hidden beneath the waves. Submarines, those silent hunters of the deep, rely on a combination of sophisticated technology, meticulous planning, and a healthy dose of good old-fashioned seamanship to find their way. Enter sonar, short for sound navigation and ranging. This ingenious technology, first developed during World War I, has become the eyes and ears of the submarine fleet. Sonar systems, housed within the submarine's hull or towed behind it, emit pulses of sound waves that travel through the water. These sound waves, like invisible ripples spreading across a pond, bounce off objects in their path, the seafloor, underwater mountains, even other vessels, and return to the submarine as echoes. By carefully measuring the time it takes for these echoes to return, and analyzing their characteristics, sophisticated computers can create detailed images of the underwater world. Think of it like an ultrasound for the ocean, allowing the submarine crew to see through the darkness and map their surroundings. Sonar systems come in two main flavors, active and passive. Active sonar sends out pulses of sound and listens for the echoes to return, while passive sonar relies on listening to the sounds generated by other vessels to build a picture of the underwater environment. Silent running. The perils of underwater navigation. Navigating in the ocean depths is not without its challenges. The underwater world is a dynamic and often unpredictable environment. Ocean currents can push a submarine off course, while underwater mountains and trenches create hazards. Avoiding detection is crucial for submarines on missions. Submarines rely on inertial navigation systems and sophisticated charting software. It's like piecing together an underwater jigsaw puzzle. Human skill and judgment remain essential. Powering the deep from diesel-electric to nuclear reactions. Early submarines relied on diesel-electric propulsion. Diesel engines for surface cruising, electric motors for silent running underwater. This system had its limitations. Submarines had to surface frequently to snorkel. Nuclear power revolutionized submarine technology. Nuclear submarines could remain submerged for months. They could roam the oceans at will. Nuclear propulsion increased speed and range. Nuclear submarines could achieve speeds over 30 knots. This allowed for rapid deployments and vast patrols, but nuclear power also brought safety challenges. Submarine reactors require meticulous maintenance. Disposal of spent nuclear fuel poses environmental concerns. The silent service espionage, science, and the future of the deep. Submarines, often referred to as the silent service, play a critical role in both military and scientific endeavors. In national defense, submarines act as stealthy sentinels, gathering intelligence and deterring aggression. Armed with torpedoes and missiles, they project power far from home shores. But submarines are more than just weapons of war. They serve as invaluable tools for scientific research, exploring ocean depths and studying marine life. Equipped with advanced sensors and robotic arms, submarines collect data and observe marine life. Imagine a submarine exploring the Mariana Trench, the deepest part of the ocean. Picture it studying hydrothermal vents or mapping the Arctic Ocean. Submarines push the boundaries of our understanding of the ocean. The future of submarine technology is one of constant innovation. New materials promise to make submarines stronger, faster, and more stealthy. Autonomous underwater vehicles extend their reach and capabilities. Who knows what other technological marvels await us in the depths? Perhaps one day submarines will carry us to other planets exploring alien seas. A triumph of engineering, mastering the underwater realm. Submarines thrive in an unforgiving environment through physics and engineering. Their buoyancy, resilience, and navigation are marvels of design. Ballast tanks control density, mimicking water displacement. Submarines withstand immense pressure with high-strength hulls. They navigate the depths with precision, turning the ocean into a highway. A testament to human ingenuity, they withstand nature's extreme forces. Echoes of the deep, the enduring allure of submarines. Submarines embody adventure and exploration, captivating our imaginations for centuries. Gliding silently through the depths, they reveal a hidden world. Towering underwater mountains, vast plains and deep canyons, strange creatures drift through the darkness illuminated by bioluminescence. Submarines map the seafloor and study marine life. They are silent sentinels ensuring security and future exploration. Into the future, the uncharted depths of innovation. The journey of submarine technology is far from over. Current innovations shape the submarines of tomorrow. Imagine submarines with lightweight, strong composite materials, gliding with greater speed and agility, their acoustic signatures reduced to a whisper, powered by revolutionary energy sources, equipped with artificial intelligence, navigating challenging environments with minimal human intervention. These are glimpses into a future where engineering and imagination blur, driven by our insatiable thirst to explore the unknown. The ocean depths hold countless secrets waiting to be unlocked. Submarines will continue to be our vessels of discovery, carrying us ever deeper into this underwater frontier. So the next time you gaze out at the ocean, remember the silent world beneath. A world of wonder and possibility, where submarines continue to roam and explore, pushing the boundaries of human achievement and reminding us that the greatest discoveries are often found where we least expect them. If you like this content, please comment, like, share and subscribe.